few more subjects which I mean, very few more subjects which I wanted to discuss in kinematics. One of those is that I mean, something which is actually quite important about this, how we look at the world, or the universe even. Because soon we will see how from the view of the universe we can predict what will happen to objects. However, we will have to look from in an appropriate way. So and it is because, depending on this, from what point of view we look at the surrounding, it appears different. For example, if I look at the finger, at my finger, and I walk in this classroom, can you imagine how I see the finger? What the finger is doing? Stay still. Yeah, I can even turn around, and the finger stays still. So from my point of view, it doesn't move. From your point of view, it moves. Things can even happen in a more drastic way. I mean, think what will happen if you put a coffee mug on a dashboard of a car and then make a turn. If you look from the inside of the car, you will see that mug accelerated. If somebody looks from the street, he or she will say that it just went straight. So and so on. I mean, we can see various situations, even differently recognize various interactions, which we will learn in the future. One person from one point of view will say that objects interact magnetically. Another person will recognize that no, this is electrical interaction. So we have to be able, and actually, when you are trying to predict something, try always to imagine yourself in the simplest point of view. All right. So describing phenomena from various points of view, and how those two points of view are related, because indeed, if you have a description of a phenomenon in one, from one point of view, or more precisely, I will call it just from one reference frame, you can predict how it is going to look in another reference frame. Or if one person is doing something and another person is doing something else, and they both watch the same at the same thing, the relationship between the view of one person and the view of another person on that phenomenon is referred to as the transformation. So today I wanted actually to introduce, well, the simplest transformation referred to as Galilean transformation, and it is a transformation between, I mean, it will be important transformation for analyzing interactions, well, if one reference frame is related to another reference frame through a Galilean transformations, then they are equally good to predict the future, and the descriptions are going to be the same. It's not like, for example, car and the street. A turning car is not related to the street through Galilean transformation. Therefore, things happen differently. If they are related through Galilean transformations, we believe so far that the descriptions are the same laws. Everything will obey the same laws, which is actually not true either, because well, modern physics actually violated that, the Galilean transformation. So we introduce a more general, now we use more general transformation called Lorentz transformation. And Galilean transformation is only good if the 2 points of view or 2 observers move relatively slowly with respect to each other. If one moves fast with respect to the other one, then Galilean transformations are invalid. We will have to use Lorentz transformation. However, unless you are on spaceship Enterprise, you shouldn't worry about Lorentz transformations. Galilean transformations for engineering will be sufficient. Therefore, it is good that you learn how to use them and what are the consequences of Galilean transformations and make predictions. All right. So now we will now relate motion in 2 reference frames related by Galilean transformation. So let's say that we have 2 observers. Here's one observer and here's another observer. And let's say that they both observe motion of another object. Let's say that it's particle P. Now, recall how we choose a position vector. How do we assign an arrow to a position vector? So if I have a particle and I want to describe position, how do we do that? A what? Oh, x, y, z are not necessary. X, y, z are already needed to assign scalar components. But just to assign an arrow, we don't need the axis x, y, z. However, you are right that we need something from that. The reference point, the origin, correct. And now how do we pick it? Where do we pick the reference point? We say? However we want. Okay. Well, it is so. Pick a point. Very good. A corner of this room, for example, right? Now, why the corner of the room? Can it be the tip of your nose? Sure. All right, I'll pick tip of my nose then. And then now, so if I consider that, what are you doing now? You are moving. From my point of view, you are moving. And actually, if I walk that way, which makes my reference frame related to the reference frame of the classroom to be related by the Galilean transformation, my point of view is as good as your point of view, or the point of view from that corner. None of those reference frames is more important, and I know that it is something which is counterintuitive. I mean, this was so counterintuitive that actually, as a humanity, we were looking for the most important reference frame in the universe. There was a time, probably you heard about reference frame of the ether. We were looking for that about over 100 years ago. And we failed. We recognized that there is no most important universe in the reference frame in the universe to which we wanted to say that this is the stationary reference frame. There is no stationary reference frame. Each reference frame is moving in another reference frame. The reference frame of the classroom, show me, can you recognize that the reference frame of the classroom is moving? How? The Earth is rotating. Correct. For example, it is rotating together with the surface of the Earth, right? Oh, well, it is rotating, it means that it is rotating in something, right? In what? The reference frame of the Earth, the center of the Earth. Oh, no, I mean, it can't be, because, I mean, I can choose z-axis to go through Kansas City and y-axis to go through something else, and then the room will not move. But in the reference frame of the stars, for example, we are moving, right? Although the reference frame of the stars is moving in the Earth's reference frame. All right. So I will pick 2 points, and let's say that from this reference point, I can recognize that this one is moving. I mean, in principle, I could do the other way around, but I always will have such a situation that from one reference frame, the other one is going to move. So in a way, you can actually think that this is the kind of stationary reference frame. But I mean, if you think about your stationary reference frame, it should be the one with the tip of your nose, the one which your reference frame is the most important reference frame, by the way. I mean, for each of you. Why? Because this is how you see the world, right? It is not the most convenient reference frame, but for you it is most important reference frame. All right. So let's try relate the motion of the same object from 2 reference frames. So let's say that relative position of one reference point to the other reference point is r, and actually Galilean transformation refers to a situation in which that reference point moves with respect to the other one with constant velocity, which means that this position vector, derivative of this position vector with respect to time, is a constant. Constant what? Well, constant velocity, right. I mean, is it a vector or a number? Vector. Velocity is a vector, which means that this constant contains 3 constant numbers: x component, y component, and z component. We have a comment or question. Can you shout?
Was it a vector because it also had direction? Why wasn't it just a number?
What number then? When we calculate, no, it is not because it has direction. It is because position is a vector. When we divide a vector by a number, we get a vector. So no matter if it is obvious what is the direction of that derivative of not or not, it is going to be a vector because of the rules of multiplication of a vector by a number. All right. I can now recognize that if I look at these arrows over here, position arrows, then the position which is observed by this observer is equal to the vector to the sum of the other 2 vectors. I can write it down this way. Can you see that? Now, if I consider scalar components of those vectors in both reference frames, and in a particular way for Galilean transformation, which we assign scalar components in a kind of, in a very consistent way. We choose base vectors in such a way that they are equal in the 2 coordinate systems. So vector I vector in one reference frame is of the same magnitude and in the same directions and in the other one. The axes are parallel, therefore. So if we have to choose the axis to be parallel. So can you imagine how actually these 2 reference frames move? Because see that it is a very limited, very strong constraint on this, how the 2 reference frames have to move. We will see what will happen in the future, what will happen if they don't move that way, because in a very general way, that motion could become very crazy. So let's say that we are thinking about, because you picked already reference frame at the reference point at the corner of this classroom. So how about if we choose that this is x direction, y direction, and z direction? So if I wanted to be that other observer, I would have to choose x direction in this here, that way, y direction that way, z direction up, and move like that. Now the two reference frames are related through Galilean transformation. Well, if we choose base vectors in such a way, and on top of it, we assume also that it is possible to measure time identically. Lorentz transformation says that it's not possible. We don't measure time identically, and there is an equation which says how to convert time measured in one reference frame with the time measured in the other reference frame. You probably already have heard about twin paradox. Those of you who haven't, it was well, kind of so far mental experiment, although for at least for people, we have already performed this experiment for other objects, and we indeed see that that it is true. But twin paradox says about two twin brothers, and one gets into a spacecraft, flies for a year in one direction with speed close to speed of light, and comes back to the Earth. And when he gets out from the spacecraft, well, he would age by 2 years, and he recognizes that his brother is 50 years older. So time did not pass at the same rate. What I described over here is still not a paradox, because the paradox is which brother should be older, but it's another story. Important thing is that one gets older than the other. So this is what the twin paradox is about. And time in the two reference frames are related by Lorentz transformation is not measured the same way. All right, so if we have these assumptions, then that relation is valid not only for the arrows, but also arrays of scalar components. I mean, you can actually try to imagine what is x component, well, how about y component? Y component of this point in the two reference frame, relate them. So y component in this reference frame, it will be like about here, right? And can you recognize that it is y component of position of this reference point plus y component in that second reference frame? Can you see that? Consult with your neighbor that you understand, to make sure that you understand what I'm talking about, and what's the difference between this and this. Talk to each other now for a while. So I want to make sure that everybody is following me. So discuss why this is true, and why did I even bother bringing this thing up? The discussion is not vigorous about, which means that probably you are confused. So how about if we think about plane? I'll make it in a plane. So let's say that this is y and z, and another reference frame. No, that one is prime. All right, I have a point over, I pick point over there. What is position? So here I will have position vector in the primed reference frame. Well, scalar components are x prime and y prime. Let's try to put unit vector. So let's say that this is unit vector I prime, and this is j prime. So what are the scalar components of vector r prime? Yeah, I have 1, 2. So x is 2 and y is 1. Now I have to choose these unit vectors the same way. Now these are I and j. Here's I prime and j prime, right? So position, this is the position vector of this reference point with respect to this reference point, and scalar components of this vector will be, let's say, 1, 2. Well, what are the scalar components of this position vector? I have 1, 2, 3. 1, 2, 3. Now, look that this 3 is 1 plus 2. Right? Now, this 3 is 2 plus 1. Oops. I can recognize that vector R is equal to capital R plus R prime, scalar components. Do you see that it works? Now, I'll show you how it doesn't work. Let's say that I will not choose I, j, and k to be equal in both reference frames. So I will make this coordinate system like that. Which means that vector R prime has different scalar components. It doesn't have 2 and 1. What are the scalar components of vector R prime now? No, first is x, right? So it is 1, negative 2. Is this now true? No. You see that? All right. So I hope that you comprehended it properly, and now you recognize that if we choose the two reference frames to be parallel, then this relationship is also valid for that one. Actually, over here I took advantage of it. It's probably I'm confusing you by the fact that instead of having r of t, I put velocity with which this reference frame moves multiplied by time. This product is really position of primed origin with respect to unprimed origin, assuming that the primed origin moves with constant velocity with respect to unprimed. Do you see that? Is it clear? Okay. So here I use already the fact that the rate of change of this vector is constant. It moves with constant velocity u. All right. Let's now see how velocities are related. So what do I have to do in order to extract velocity from position vector? Say it in English. I have to calculate the derivative, or just in one word, I have to differentiate position vector. Correct. Calculate the derivative of position vector. And the reason that I wrote it explicitly that position vector is equal to velocity multiplied by time is because it's easier now. I mean, I know what will happen with the derivative. It's a constant times time. Derivative will stay just a constant. Derivative of this, I mean, precisely, actually, I should have here r prime t prime, because obviously if I walk, I don't watch, I look at my watch, not your watch. So I use here also the fact that the two times are identical. We can measure times identically. So I can recognize that velocity in one reference frame is related to velocity with another reference frame, and we have to add just the relative velocity of the two reference points. But the most important part is the next one. I want now to relate accelerations. See how accelerations are related. So what do I have to do now? Differentiate velocity. Correct. So if I differentiate velocity, from this expression I will get acceleration in the unprimed reference frame, and from this expression I'm going to get acceleration in the primed reference frame. Well, so the conclusion is that if reference frames are related by Galilean transformation, accelerations in the two reference frames are identical. It will be very important in the future when we start talking about Newton's second law, because Newton's second law will say that how to relate or how to figure out from configuration what is the acceleration. And that equation now says that it doesn't matter in which reference frame we are looking at the situation, except that they both have to be related by Galilean transformation. So, for example, I already mentioned the reference frame of a car with the cap on the dashboard and the street. The car, reference frame of the car is not related by Galilean transformation with the reference frame of the street. And because of that, we can recognize that from the street it appears that the cap is not accelerating. In the reference frame of the car, it accelerates. It accelerates to the other side and to the other direction than you turn. All right. Now, I want to clarify the difference between speed and velocity, and I know that all of you already know this fact that that speed is equal to the magnitude of velocity. But then when you think about velocity, you think that it is speed with a direction. I don't want you to define these two quantities that way, because it is like defining that a dog is not a cat and cat is not a dog. Do you understand me? What is the definition? What is velocity, by the way? I like it. I don't like it exactly, but this is really what it is. It is change of position divided by change on time, but it has to be infinitesimal, which means that actually it is. I don't like that. It's derivative of position. Derivative of position, or the rate of change in position, is velocity. Now, when we understand the velocity in this particular way, we can figure out what is the magnitude. So magnitude of that particular vector is going to be speed. So don't now define velocity in terms of speed anymore. All right. Now, I want to bring up a few facts which actually result in the confusion. Well, so speed is equal to the rate at which the particle moves along the path. It is not the rate at which it is displaced. It is how fast it moves along the path. So, for example, if I walk like that, what was my displacement? Zero, correct. Now, is the length of the path zero?
No.
No. right? Now, velocity is related to my displacement. Speed is related to the length of the path. All right, let's take a look at that it is really, this theorem is valid. So let's say that the particle here has a certain velocity, or let's consider an infinitesimal time in which that particle moved by displacement dr. Well, if we want to find out speed, we have to find magnitude of velocity. And can you remind me? I mean, actually, you have already a hint over there. How do we find magnitude of a vector? Square root of a vector square. Which square? Which square of the vector? Not x component. We have to square entire vector. But how do we square a vector? Using scalar product, correct. So it is vector times vector using scalar product. How many products do we know so far? 3, good. All right, so I wrote it, and just to make sure that we recognize that it's a scalar product, I used the unambiguous notation over here. The book doesn't use it, so be careful about it. And soon I will stop using 2, assuming that you grasped it and that you are not confused. How to recognize, if I don't use unambiguous symbol for multiplication, that a product is a scalar product. How to recognize that in notation? Because there are arrows above the vectors, correct. So if I have vector multiplied by vector and dot between them, I do not confuse it with multiplication of numbers because there are 2 vectors. Make sure, however, to put a dot, not a cross sign, because cross sign is used for another product which we don't know yet, but we will learn it soon. All right, because in high school you were using cross for multiplication interchangeably with a dot. Now, be careful from now on. All right. Well, because of property of scalar product, I mean, what happens if I multiply a vector by a number, I can actually recognize that square root of a quotient is equal to quotient of square roots. So here I have square root of vector dr times vector dr, and here I have square root of dt times dt. Didn't I make a mistake here? No. Very good. Why not? Because these are 2 numbers. Over here we have indeed two vectors. Now, square root of vector dr times vector dr gives me what, really? In other words, what is the dl? It's the magnitude of that vector. So if I now think about, well, what is a magnitude of that arrow over here? It's the length of it, right? So it means that it's that, well, kind of, length of this differential path. So here I have the length of the differential path divided by the time. This is what speed refers to. Well, if I reverse this relationship, I can recognize that if I know the speed everywhere, at any instant, this differential path length, dl, is going to be speed multiplied by dt. Can you see that? So if I integrate it over particular interval, what am I going to get? How about if we come back to the whiteboard? Now think about integrals that it's a sum. What is the shape of it? Okay, like that. Now, the length of this fragment of the path is equal to speed at this instant multiplied by time it took to get from here to here, right? Now, So if I add all of those dLs, which means that I will have integral, over this entire path. So it will be integral from, let's say, this is point A, this is point B, from instant when the particle was at point A to instant when particle was at point B of speed with respect to time. Well, it is equal to that, but it was a digression. Think what will happen if I add all of those dLs. What am I going to get? Length of this entire path. So this, let's call it, this is length of the path from A to B. I know that this symbol, that you don't really think, you still think about integral like it is something very foreign for you. Now, this symbol resembles a letter. Can you see that? What letter? S. Why? For the sum. Correct. Think about integrals, definite integrals. We will deal most of the time with definite integrals as the sum. Right? Do you recall that what I said yesterday about integral, that I feel it like it is the sum of all values of the function between the limits. Think that way about the integral. So this is addition, really. Integration is really addition. The difference between, why do we use integration rather than addition? Because we are integrating uncountable number of numbers. This is the only difference between the sum and integral. In the sum, we have countable number of terms. In the integral, we have uncountable number of terms. Well, I want to bring up two more concepts associated with integrals. Average, which I discuss in the chapter, average velocity and average acceleration. Actually, we can think also about average speed or average in any quantity. Whenever we have a function, we can find an average value. And if I have a certain function, by definition, we understand this expression to be the average value. You just can memorize it. So average value of the function over an interval AB is equal to the integral of this function over that interval divided by the size of the interval. Now if I take a look at the size of the interval, so geometrically, now what we can think about is that integral represents the plot, the area under the curve. So this is what integral has. Now average value, look that if I multiply both sides by b minus a, I will have average value multiplied by b minus a, which means that this dimension here, I will get the same area. Yeah, the product of this size multiplied by the average value should give me the same area as this plot. Well, which means that area of this rectangle has to be equal to the area under the curve, the plot. This is geometrical interpretation of the average value. Now, I wanted to bring it closer to your intuition, because what is your intuition about average value? And as an example, I will give you a puzzle. Let's say that yesterday, through whole day, my balance was $10 on the checking account, and today $30. What was my average balance? 20. How did we do that? Added them and divided by 2. All right, now let me complicate it a little bit, and let's say that I had $10 yesterday, and $0 2 days ago, and I have, what did I say last time? 20 today. What would be my average balance over those 3 days? 10, right? You added 0 plus 10 and 20. Well, how about if I had $10 for 2 days and $20 for 1 day? Not 10? How much? 15? Who believes that it's 15? Those of you who believe that my balance was not 15, you are right. I don't think so. 13.3. But I mean, you're on the right track. I know that you are on the right track. Yeah, because yeah, so I had $10. I would have to add 10 for the first day. I have to add 10 for the second day and 20 for the third day. So the sum is going to be 40, and I have to divide it by 3 because there were 3 days. Well, actually, this is the same procedure. You can recognize that actually b minus a is the sum integral of 1 interval from a to b. So you can think that the b minus a is a measure of number of points in the interval. Yeah, the more, if I double the number of points, b minus a will double, right? I mean, if I take a longer interval. So what I have over here, and particularly look at this, what I said about my interpretation. Over here, I add all the values of the function and divide by the number of points of the arguments, right? So this is the same average which you know. It is just generalized to a case when you have uncountable number of values. Aren't we smart as humanity? I mean, see how neat thoughts we have to think. All right. Let's now take a look at average velocity. So let's say that a particle moves along a certain path. Well, at each point it had a certain velocity, or at each instant had a certain velocity. So consistently with the definition of an average value, I will have to add all velocities, and velocities at all instances between this instant and that instant, and divide by the number of instances. Now, using fundamental theorem of calculus, this integral is equal to what? Not velocity at the 2 instances. First, yeah, because fundamental theorem of calculus first asks us to find indefinite integral of this function. And in other words, a function whose derivative is velocity. You have an idea. Position of the particle has this property that if I differentiate position, I'm going to get velocity. So position is an indefinite integral of velocity. And when according to fundamental theorem of calculus, I have to just plug in those 2 values. So position at instant corresponding to the end of the interval minus position at the initial instant. Now, difference in position is referred to as displacement, correct. So here I have a displacement from this instant to that instant. I can recognize now that really what I'm calculating here is change in position in that time from t1 to t2 divided by the time it took place. And actually you recognize that this is the high school definition of velocity. In high school we didn't think about tiny tiny values or tiny changes. That's not how we had to think. So ratio of displacement over time results in the average velocity. All right. So coming back to this experiment, when I walked like that, what was my average velocity? 0. Do you see that? Because the displacement is 0. How about average speed? Positive, negative, or 0. Some number is too vague. Yeah, it could be positive, negative, or 0. Which one is it going to be? Some positive number, correct. Now, you can recognize that all the time I had a non-negative speed. So if I add those numbers and divide it by the number of instances, I will get some positive number. Well, I hope that it makes a good example for distinction between velocity and position. And by the way, if I to what velocity is related and to what speed are related? Let's recall that. Velocity is associated with displacement, correct. And speed? Well, it's magnitude of velocity. How about something related to displacement? Yeah, because here is a problem. The problem is confusion length of the path with displacement. Yes, speed is related to the length of the path. Velocity is related to displacement. All right. Now, the last part is, how about if we consider accelerations? Average acceleration. Again, we'll have to add all accelerations and divide by the number of instances. Now, can you find an indefinite integral of acceleration? Velocity, correct. So using fundamental theorem of calculus, this integral is equal to the difference in the two velocities at the end of the interval and at the beginning of the interval. I can write, well, how about if we take a look at this? So I have from that velocity at instant t2, I have to subtract velocity at instant t1. It was, well, to the left, so here I will have to the right. Here is the change in velocity. And if I divide it by time, I will get acceleration. So ratio of the change in velocity over times results in the average acceleration. This is also high school definition of acceleration. Now we are in calculus-based engineering physics. Therefore, acceleration for us is, what is it? Derivative of velocity or rate of change in velocity. All right, so this will be all for today. Thank you very much then.